Yeah, so my talk is called Applications of Non-Intrusive Load Monitoring to Power Systems and New Non-Intrusive Load Monitoring Type Problems. And this work is supported by NSF, ARPA-E, and the Department of Energy. So you can, interesting. Okay, I think I have everything working now. So as a disclaimer, as Mario already said, that this is not my field. So non-intrusive load monitoring is something I've dabbled in, but it's not my field. I'm not an expert. I primarily publish in the field of electric power systems, and I have a background in control systems. So this is coming from an outsider. I will also say that I first learned about non-intrusive load monitoring in 2011 when Mario visited Berkeley Lab. I was an affiliate there and a student at Berkeley at the time. And so he sort of expanded my world to understand a bit better about all the different problems people work on with respect to electric loads. I do think about electric loads a lot, but from the context of power systems, specifically how to harvest flexibility from loads to help out the power grid. I started working in the field of demand response, and now I work in the broader field of power systems and also think about the power network as well. So thanks for inviting me to give this keynote. So when I say harvesting flexibility from electric loads, I just wanted to sort of paint the picture of what I mean here. So a lot of my work has focused on aggregating loads and coordinating them to provide services. And this is actually a figure from an ARPA-E project that we have going right now. So you can see over here on this side, this is supposed to be basically just a control diagram. We take a bunch of loads, and specifically I look a lot at thermostatically controlled loads like air conditioners and water heaters and refrigerators. We want to control them such that their aggregate power consumption tracks the balancing signal in the grid. So this is how a control engineer would sort of think of the control problem in the block diagram. And here you can see the power output. So here, if the loads are not being controlled, they would follow this blue line. And instead we want them to track a signal that goes up and down around that blue line, such that the total energy consumption over the course of several hours is about the same as it would have otherwise been. But we increase and decrease loads at key times to track a signal like a frequency regulation signal. And then the information on the bottom is just what we're focused on now. We're trying to understand how to do this type of load coordination while making sure that we're not aggravating any problems in the power distribution network, that we can handle communication networks that are sending information back and forth to the loads that aren't perfect, because most of these networks are have delays and other issues. And we also want to make sure that when we're controlling loads that we don't cause instabilities. So this is sort of one of the key problems that I like to think about. And so you could say, how is this connected to non-intrusive load monitoring? Well, to solve many load coordination problems, we need models of the loads, and we also need real-time feedback from the loads. So that means that we need both offline and online data from the loads. We can get that, of course, from submetering, and we can also use home energy management systems to control houses sort of at the point of connection to the grid. But all that stuff isn't pervasive yet, as this field, of course, knows very well, which is why you're interested in leveraging meters sort of at the household point of interconnection to understand the loads within the house. And we would like to do the same thing to leverage these resources. So the question is, can we then incorporate non-intrusive load monitoring inside these sort of demand response grid services type problems? So applications of non-intrusive load monitoring in power systems are very diverse and widespread. And I think that probably a bunch of people listening to the talk have thought about this from some perspective. The way I would classify these applications are sort of, again, breaking it into offline problems that we need to solve and online problems. The first one here is that we need models, and specifically to solve control problems, we need dynamical system models of loads, which we can build from data. And we need those sorts of models so that we can represent load in planning studies, but also to use in real-time grid operational strategies, real-time and in advance. So the grid sort of, we like to solve different problems on different timescales, but we often solve optimization problems a day to a few hours in advance to decide how to plan what we will operate on the grid, and then real-time control problems to constantly be correcting for forecast error. So both of those need models of loads. We also need models of loads to estimate their flexibility and availability for providing grid services. And there have been some papers that have looked at this. So how you can use non-intrusive load monitoring to estimate how much of a certain type of load might be available. so that you can then offer that capacity to the power system operator to provide a service like demand response. You can also use non-intrusive load monitoring for verifying the load response. So after there's an event, when you ask a load like an air conditioner to shut off, you can look at the smart meter data, for instance, to see if it actually responded the way you expected it to. And lastly, I think the one that's the most exciting is to get real-time feedback of the load response from the smart meter data or the existing meter data, so that you can understand if the load's responding the way you're trying to actuate it to respond. So that if it's not responding, you can change how you're sending that control signal out to get it to change its behavior and hopefully respond more in line with what you were hoping. So there's lots of these sorts of applications, and a lot of my work sort of assumes that we can use non-intrusive load monitoring for these sorts of problems, but there's also other types of problems that are very related to non-intrusive load monitoring, but I think are a little bit different in scope and size. So one example is disaggregating load at points other than the household meter. And there has been significant recent work in trying to understand solar PV generation and distribution networks using measurements that are taken at substations. And so solar PV generation, you might say, oh, that's not non-intrusive load monitoring because solar isn't a load, it's generation. But power engineers like to treat solar PV as a negative load because it's not very controllable, and that's sort of how we distinguish between load and generation. So these papers use feeder measurements, so measurements taken from the distribution network to understand how you can pull apart the solar PV generation from the load in the network, and that helps with a variety of different planning and operational strategies. But even broader than that, we can think about disaggregating load on a feeder by its type, where some of that load is solar PV generation, but we might also be interested in understanding things like what's the current load of the electric vehicles on the feeder or the air conditioners. So a lot of my work has been looking at air conditioner control. In fact, the ARPA-E project I mentioned, we're trying to control air conditioners to provide frequency regulation to the power system. So we want to understand how much the air conditioners on the feeder are consuming at a specific time. So what does that look like? This is a little bit of a visual representation of what I was just talking about. So this blue line is the net load measured at the substation. And this is something that a utility would have a good measurement of. They have to monitor this to understand if they're operating within the limits of their network. And so this is something that's measured and can be measured at fairly high resolution. But it's an aggregate load of potentially hundreds to thousands of households and businesses and different things like that. And so it's kind of smooth, like I've shown here, and it has some variation, diurnal variation. So this could be the load over a day. And what we might want to do is pull that apart. So the studies that I showed you before are trying to pull out the solar photovoltaic and feed. So that is a negative load. So I've shown it here as a negative. And then there's other loads on the feeder, like the electric vehicles and air conditioners that I was just talking about. And then there's everything else that's being consumed. And if you were to add up all of these different colored lines, besides the blue one, they would add up to the blue one. But how do you pull this apart into its different types? And that's the problem I've been working on for the past couple of years through an NSF funded project, specifically motivated by understanding how we could use this sort of pulled apart signal as a feedback in a control algorithm for controlling air conditioners. So you all know this stuff better than I do, but I'd like to sort of explain how I see the classical energy disaggregation problem differently from the problem that we're posing here. There's lots of references here. They're a little bit old at this point, and I'm sure you guys have worked on this problem quite a bit. But the way I think of this problem is that you're estimating the individual loads of different appliances in the house from a single power measurement. A lot of the methods use very high frequency data from the household main, as opposed to smart meter measurements, which are usually much lower frequency. Of course, there are a bunch of newer papers that have looked at leveraging low frequency smart meter measurements as well. And then there's a variety of methods used to solve this type of problem. The key differences with this feeder level disaggregation problem are that we're assuming that the measurements are at the substation, not the house. We're estimating the power consumption of all loads of a specific type. We're not breaking down the load by by individual appliance, for instance, but saying what's the load of all the air conditioners, what's the negative load of all the PV generation right now. We want to solve the problem online, not offline, because we're going to be using it for feedback in a control problem. And we need to use lower frequency measurements, usually taken every second to minute, not very high frequency data. And what actually helps us, so a lot of these things hurt in the sense that it's actually pretty hard to see what's going on in the feeder when you have such an aggregate measurement, because it's that smooth signal I showed you before. How do you pull that apart into its components? That's pretty hard to do. But what might actually help us is that in a lot of these cases, because since we're applying some kind of demand response algorithm and controlling these resources, we might get to be intrusive in the sense that we could send control signals to learn better. And so there's these nice ways of formulating this problem as well, where you can think of it as a combined learning and control problem, where you get to, send control actions that both try to achieve what you want in terms of the control of the network, but also help you learn. But in this talk, I'm not going to talk about that specific piece of being intrusive. I'm just going to assume that we're sort of not controlling the network and trying to disaggregate the feeder. So why is this important? I've alluded to this before. We want to use it for demand response, but in these, there's been a lot of papers that have assumed that the control system looks like this, where you leverage a measurement of the aggregate power consumption of a bunch of loads that you're controlling, feed that back into the controller, and use that to try to track a reference signal by computing an input to the system. But that requires that you do have a measurement of the aggregate power consumption of the loads. And when these loads aren't all in the same part of the network, you might not have a meter that's measuring that. So the sort of brute force way of getting that measurement is to measure the power of every single load you're controlling, send it back up and aggregate it. But that requires a communication infrastructure and a measurement infrastructure that might not already exist, especially if you're controlling a load that isn't sort of already submetered in your system, which is true in some cases for air conditioners. So if you can get the control signal out, but can't get the feedback back, instead we often say, let's assume that we can take a measurement in the network. So we'll take a measurement at the substation. That measurement includes the aggregate power of the loads you're controlling, plus everything else that's happening. So a lot of papers have said, well, we're going to estimate that everything else that's happening and subtract it out from the feeder measurement, and that's going to be the aggregate power of the loads you're controlling. Is that a good assumption? It's not quite clear if that's sufficiently accurate, but a lot of these control strategies assume that measurement is noisy. But in any case, if you could do this in a more sophisticated way by doing this sort of energy disaggregation where you estimated the consumption of all the loads you're controlling, you potentially could do a better job of then controlling the loads. So that's kind of the key thing that made me start working on this problem, because I was interested in how you get a better estimate of the aggregate power consumption. But you can also use this sort of approach to understand how much a load aggregator could bid in terms of the resource of controllable loads. And a utility could also use this information to figure out when they should call a demand response program. Because if they have an estimate that there are more electric vehicles or air conditioners on their network than usual, and they're expecting that there might be voltage problems, they could trigger a demand response event if they could kind of see the breakdown of the loads a little bit better. It would give them more information for how to call that event. And then beyond demand response, breaking up the load by type can also help for a variety of different applications. The first one here is a strategy of conservation voltage reduction, where you're trying to sort of improve the efficiency of the system by reducing the voltage in a strategic way to reduce the consumption of the loads that actually consume power as a function of voltage. But to do that effectively, you need to understand how the loads are going to respond to that change in voltage. So if you could disaggregate the load by type, specifically, we call different types of loads zip loads with different components for how responsive they are to voltage. You could do a better job of triggering conservation voltage reduction in that case. And then you can use this sort of disaggregation for a variety of different types of planning problems. Motor loads can cause stalling or can stall if there's voltage problems in the network. That can cause a variety of different issues. So if you could disaggregate motor loads, you could have a better picture of if the network is going to experience voltage problems. And then lastly, of course, you can disaggregate solar production, like in those papers I showed. So there's a variety of different methods to do this. You could use a short-term forecasting, load forecasting technique, but that doesn't incorporate real-time feedback. A control engineer would want to use a state estimation technique. So that's what we actually started with. But the sort of techniques that leverage nonlinear system models can be very computationally intensive and most of the models that we want to be using are nonlinear. You can also use online learning. It's typically, data-driven, model-free, although there's now a lot of folks working on combining online learning with dynamical system models, and that can help you leverage information you might have about your system and make decisions that are sort of more intuitive because they're based on models. So we're taking a hybrid approach in this paper where we use an online learning algorithm. There's actually two parts of the algorithm, dynamics fixed share and dynamic mirror descent, but it leverages system models, dynamical system models. Fortunately, they can be of any form. We're not optimizing over the models, we're just evaluating the models so they can be nonlinear. But we use an optimization-based approach then to determine which models are performing well and which ones aren't to improve our estimates. So I'll talk a little bit about that next. This is the outline of sort of the rest of the pieces of my talk. We'll talk about how we're solving this energy disaggregation problem at the feeder. And then the two papers that this first part is based upon are shown here. So here's the framework for the problem. The text at the top here sort of summarizes it very briefly. We get to measure the purple, which is the load at the feeder, and we're estimating the blue, which is the air conditioner load in the network, because that's what we want to use. That's the information we want to use in our control algorithm. The orange is the rest of the load in the feeder. So you add the orange and the blue, you get the purple. So in this very simple setting, we're just taking one measurement and pulling it apart into two estimates. If you just look at this at a snapshot in time, you don't have enough information to do that. But if you know something about the dynamics of your system, then you can more effectively pull these things apart. So the approach we use has two pieces. The first piece is that we have to generate models of our system, specifically models of the aggregate air conditioner load and models of everything else, all the other load. We'll call it other load from now on. So we have these sort of models and we leverage those models to come up with estimates. But those models get fed into this algorithm. So this slide is showing how we do estimation in real time. So all the models exist in a model bank. And that model bank, we use each of the models to, and we apply this algorithm, dynamic mirror descent, to come up with individual predictions of all of the aggregate air conditioner load. But we do that for each of the models. And then we send those predictions to this other algorithm, dynamics fixed share, which combines those estimates by basically weighting models based on their historical performance. So that's how this overall approach works. And then mathematically, this is what it looks like. So dynamic mirror descent. First, we have an observation-based update where we have L is a convex loss function and D is a Bregman divergence function, where we're basically the takeaway here is that we're trying to make sure that our algorithm is basically matching the measurements, or our models are matching the measurements, and they're also not diverging too much from what they were in the past. So we use, based on an observation of the system, we update our estimate of a state. And then we use a model to further update that estimate. So we use the model to basically predict what's then the next state for our system. And then the dynamics fixed share algorithm takes all of the predictions across all the different models. So you can have hundreds of models, each creating these different predictions. And then we weight, we basically come up with a weight for each model based on its historical performance, but we're sort of weighting it based on performance, but also we give some emphasis to the average prediction of all the models, because we don't want to put too much weight on a single model if that model isn't going to be consistently good over time. So we want all the other models to be able to sort of come back and give their estimates if they become good at different times. So different models are weighted higher at different times over the course of the dynamic simulation. And all those weights get combined here together with the estimate to come up with an overall estimate for the system. And in the paper, I won't go into too many details on this, but they do provide some algorithmic guarantees in terms of regret, which is the performance with respect to a comparator. So they show that they can basically bound the regret and show that for many classes of comparators, regret scales them linearly. And I'm not going into this into too many details because for the application we're interested in, we don't necessarily care about this kind of performance. What we care about is the performance in terms of how well we're actually going to be able to predict the aggregate air conditioning load in this case. And that's what we care about, but we have no guarantees on that. And we can show cases where this works well, where it doesn't work particularly well. We sort of try to capture the range of cases, and I'll show you that in the case study results. But if you're sort of interested in these algorithmic designs, this is something that people in this field think about a lot, regret. So in terms of the case study we do in this paper, this is the plot I showed you before. We're trying to pull the air conditioner load out from the feeder measurement. But what we do is we create models. So we assume we have 29 air conditioner models that we created based on a variety of different ways of modeling aggregate air conditioner consumption. We have 6 models of the other load in the network. If you combine an aggregate air conditioner model and the other load model, you come up with one net load model, one total load model, and all the combinations of that is 174 load models. So for this paper, we investigate, the algorithm is incorporating all 174 load models at every time step and evaluating them at every time step. The other load models are very simple. We just take historical data. In one case, we just smooth previous days data and use that as a model. In another case, we use a linear regression model that's based on time of week, outdoor temperature, and previous total demand. So you can see here, the other load on a particular day is the black line. That's what we're trying to match. And each of these different models in color shows how well that model predicts on that day. And they're actually not too bad. Because again, since we're looking at aggregate load, it's a lot of the ups and downs sort of cancel each other out, right? So that it's such a large load, it's on the scale of megawatts. So it's actually reasonable to use historical data for prediction. And then in terms of the air conditioner model, so again, we're predicting aggregate air conditioner load, not individual. We also can use the linear regression model. And then we use linear time invariant and time varying system models that we've developed in past work that model air conditioner dynamics. And this is how one of them looks. So this is a standard way of representing a linear time invariant system model where X is the state, Y is the output, A and C are parameters. And this model is based on a previous paper where we model basically the transitions of air conditioners around a deadband. So here's their temperature, their on and off state. Air conditioners are off, and then they switch on when they reach a high enough temperature, and then they move down this way. You can represent all different air conditioners in the population in this state space, and basically the A parameter here is a transition matrix to show how they're moving over time. The problem, of course, with this model is it's time invariant. So that means A is fixed. So when you parameterize this model with a choice of A and C, you end up getting a straight line. So all the predictions are basically predicting. So these are, the red lines are each a different model that corresponds to a specific outdoor air temperature where we've identified A based on that outdoor air temperature. But once we fix that, all the model predicts is a straight line over time. There's no interesting dynamics that happen over time. So it's not very accurate. It's sort of precise once or twice, and then it's not accurate the rest of the time, right? So linear time varying model is much, much more accurate. So it has the same form, except that this A and C parameters are now functions of time. Specifically in this case, since it's air conditioners, they're sort of functions of temperature. The aggregate air conditioner consumption is a function of outdoor temperature. So you can see these models are much, much better. So the gray line is the actual air conditioner population's aggregate consumption. And then these different colored lines are predicting that over time based on this linear time varying aggregate model. So we'd expect these models to perform much better than the previous ones. But we include them all because the algorithm should be able to determine which ones are working well and which ones aren't. So this algorithm that we've taken is from sort of theoretical signal processing field. It doesn't translate directly to our problem setting. Specifically, the algorithm I showed you before has this parameter theta, which you should interpret as sort of like a state. But there's no notion of the difference between the state and the output. And in control systems and in these sorts of problems, we think of the output as the aggregate power consumption and the state as something else that just helps us predict the aggregate power consumption. So in the models on the previous slides, the state is for instance, like basically maps to the temperature of different air conditioners in the system and how those are evolving over time. But because there's no common state amongst all of our models, we had to update the method. So that we created two different ways of modifying this algorithm. One is to use the algorithm to update the output, and one is to use the algorithm to update the state, where we define the state differently for each model. And this is sort of like a subtlety that ended up causing a lot of trouble in just understanding how you could apply these types of algorithms to problems where you didn't have the same notion of the dynamics, let's say. But that's ended up being what we worked on quite a bit to make this work. So update method 2 that I show here is basically just using the algorithm as it is to update the state. But update method 1, because we're adjusting the output estimates based on the model predictions instead of the state estimates, what we have to end up doing is rewriting the algorithm to look like this, where basically it allows us to derive this closed form update equation to be able to update the output as opposed to the state within the equation. So I won't go into too many details here, but the details are in the paper and they show kind of how we have to apply these sorts of things. I'll also say that, for the linear time and varying system models, we have a state, but for the regression models, there's no state, right? So somehow to put all these things in a common framework was really the challenge. So for our case studies, we use realistic data to create data for a feeder, but we don't have data for a particular feeder. We sort of took it from a variety of different places. You can see here, Texas in the Bay Area, and we're using GridLab-D, which is a simulation software that we use to simulate distribution networks to sort of create something that's realistic, but not real. And we compare the approaches against the best benchmark approaches that uses a Kalman filter. So the basic idea here is this total of measurement is, what we're measuring for the feeder. We predict the other loads so that we get an air conditioner, what we call pseudo measurement. So this is what we're actually after, is the air conditioner aggregate load. And we're getting that by just subtracting our prediction of the other load from the measurement. We feed that into a Kalman filter, and then we get an estimate of the load. So we do that as a benchmark because, again, a controls engineer would have immediately gone to trying to use a Kalman filter to solve this type of problem. We thought we should benchmark against it. But not all the models allow us to sort of use a Kalman filter. We have to use an LTV or an LTI model for that. But using all the different combinations of the ones we're trying, we compute the predictions of the best Kalman filter and also do an average over the Kalman filters to understand performance. We wouldn't expect and realize that we would ever know which is the best Kalman filter to start with. So that's a benchmark that's very hard for us to achieve because it's the a posteriori best. We compute after the fact which one is the best, and we say this is the best we could have done with the Kalman filter. So benchmarking against the average is much more reasonable. So here are some results. What's important to look at is we're trying to predict the air conditioner load, but we also end up with predictions of the total load, which we also measure, and the other load, which we don't measure, but we're interested in the air conditioner load. So here's the air conditioner load over time as the gray line. And then the sort of purple pink line is what our algorithm is doing in terms of the predictions, pretty good. But the green line is what the Kalman filter benchmark approach is doing, which is also pretty good. So they're all pretty good. And so in order to be able to benchmark which is best, we can compute the root mean squared error, which is shown over here. So we want this error to be as low as possible. And we can see here for this specific case that the algorithm we're using, DFS-DMD, has the lowest error. And we actually beat the best Kalman filter. Although I'll show you later that we don't always beat the best Kalman filter because, again, it's an unrealistic benchmark. And we do much better than the average Kalman filter. So this approach has the potential to be better than a Kalman filtering type approach, which makes sense because Kalman filters are sort of optimal for linear if everything in your system is linear, but these systems are not linear.
Can I ask a quick clarifying question?
Yeah, sure.
So are these the example results for one of the 174 load cases that you have, or like?
So, sorry.
Yeah, I just want to know like how representative these are and what error bars would be. That's kind of what I'm.
I will show. Yeah, I'll show you error bars. So we were using 174 models, and in this case, all 174 models are being used to come up with this one prediction on one day. But then we predict over many, many days and compute the statistics of those. Okay. So the statistics will be over predictions, but for each day we're using all models.
Yeah, I got it.
And here you can see the model weights as they're evolving. So I'm only showing the model weights. So how basically interpret these as how good each model is as it evolves over time. So I'm just showing that for 3 different models that perform particularly well. And then the weights, the sum of the weights of all the other models are just in black because these are never working well. So initially we kind of weight everything equally, but the black is up here because that's the sum of all of the remaining 171 models.
Right.
And then you can see eventually these 2 models end up being the best, but the algorithm can't pick between them. It's still saying it's better to use a combination of those 2 going forward. And then these 2 models are using the linear time varying AC model, both of them, but slightly different versions of them, and a multiple linear regression for the other load. So those end up being the best over this specific day, but other days look different.
Okay. Thank you.
Mm-hmm. Right. So here are the statistics. So it's showing perhaps more than we really need to focus on, but the air conditioner demand is in black. So you can see the black lines here. That's what we really are interested in predicting. The rest of it is sort of just coming out of the algorithm. And here's for the 2 different update methods, 1 and 2, either updating the state or updating the output. This one is the best overall. And it's showing that, the clusters here. So M full is the full model bank, 174 models. M reduced is getting rid of all the linear time and variant system models. Those are the ones with the straight lines where you said, okay, those are no good. Why are we using them at all? It's actually better to throw them out because the algorithm gets confused because sometimes they're accurate, or just twice a day they're accurate. So it's better to just not use them at all. And M Kalman filter is using the models that can be used in a Kalman filter. So that's getting rid of all the regression models and just keeping the linear time invariant and time varying system models. So it's actually best to use M reduced. But of course, this is also specific to this case study. And this is where I get a little frustrated in the sense that these methods have performance guarantees and proofs that they work in certain ways, but never performance in the sense that we really care about. Because if you were to apply these same methods to a different data set, you might get different ordering of what's important and what's not. And if you change your model bank, if you change what models you're using, you also get different things. So in any case, this is sort of just illustrative to show you that you can do better sometimes than a Kalman filter. So the best Kalman filter is shown here and the average Kalman filter is shown here. So on average, we never beat the average best Kalman filter for any of these cases. On average, we do beat the average Kalman filter, let's say. So mean here is the mean over different days. So we're beating this case here and here, for instance. But actually, when we use the full model set, we do worse than the Kalman filters on average. So it just tells you that if you were to use this approach in real life, you would have to really tune the models that you're using to make sure that they sort of were adding something to the algorithm instead of confusing the algorithm. And this is just to say that the algorithm also requires the choice of different types of parameters. And different parameters basically tune how much you're trying to weight the average performance of the models versus the specific performance of individual models and so forth. Our case study is using values that are shown here and here, but we basically try to explore the full range of different values you could set for this parameter eta S and lambda, which were in the DMD and DFS algorithms. And it turns out that if you tune these, you can do much better. So the results I just showed you in the previous slide are for sort of this case that's not tuned. But in real life, we didn't spend a lot of time tuning it and rerunning the cases because all of this tuning is specific to the specific case study and data that you're looking at. So could you really do that in real life? I'm not really sure. But this is just to say that these results do change with this tuning and they can change substantially. So maybe if there are any clarifying questions, I'll stop there. And then I'm going to shift to 2 other quick topics that relate back to this problem that we've been working on.
Yeah, there are questions in the chat, but they will become relevant at the end of your conversation.
Okay.
I'm monitoring it. Okay.
Okay, great. So I should keep going.
Yes.
Okay, sounds good. So I just wanted to talk about 2 more extensions we kind of worked on here. One is connections with Kalman filtering. So we benchmarked against a Kalman filter, but it turns out that these concepts these concepts coming out of machine learning, signal processing, are actually very similar to Kalman filtering. So in a Kalman filter, we're assuming the model form and choosing the process and measurement noise covariance. Whereas in DMD, the model can take any form. So we can use highly nonlinear models, but we still have to choose something, this loss function and divergence function that I showed when I was explaining sort of the math of the algorithms. And you get to choose those to capture what you care about. So the loss in terms of prediction loss, like how far away you are from predicting the performance. So how should we pick these specific functions is a question. So what we do is, in this paper, is we show that if we choose these functions intelligently, we can actually make it such that the algorithm for dynamic mirror descent looks like a Kalman filter. But in order to do that, we have to leverage these covariance matrices P. So these courses, so P hat K and P hat YK are this state and output estimation error represented in a covariance matrix. And that's what's required for a Kalman filter, that you have to estimate that based on historical information. There are ways to update that using updated equations in a Kalman filter. So if we can also include that information in dynamic mirror descent, dynamics fixture, then we are basically giving the algorithm more information about performance and error statistics, and that can improve DMD and DFS. So if we do use those error statistics and rerun our cases, what we find is that we can improve the performance of these machine learning algorithms. And the main takeaway here, again, too much data, I'm sorry, is that if we assume we don't know anything about the error statistics, so basically how well this algorithm is performing over time, we get root mean squared errors that look like this. So identity, it means that we don't have any information about the covariance matrix. If we use historical information about the covariance matrix, it changes the errors, but you'll see it actually increases the error. So we do worse if we use historical data to parameterize the error statistics. But if we use real-time data to get the error statistics and then use that within the algorithm, then we do better. So if there was some way to actually incorporate error on how well the algorithm is performing over time and update that in real time, we could improve these algorithms because we'd be using more information about the system. So we spent a lot of time thinking about this and how these algorithms compare to Kalman filtering. Similarly, dynamics fixtures, which is using multiple models and combining them in this weighted estimate way that I described already, that is very similar to something called a multiple model Kalman filter. And you can construct dynamics fixture to also produce estimates up that are identical to multiple model Kalman filters. So basically, these are very, very similar techniques that we come at from, in one case, a controls direction, another case, a machine learning direction. But what you can then do when you realize that these things are the same is if theory has been developed for one, you can port it over to the other. So using error statistics, like I showed you in the previous slide, is one example. But in this case, with multiple model Kalman filters, there have been a variety of approaches to improve their performance, which I list here at the end of this slide. And you can adapt all of these for dynamics fixture as well and improve the performance of that. So the takeaway here is that the case study results I showed you before are for a specific case, kind of using things as much off the shelf as they can be used. There's lots of ways to further improve their performance by leveraging these ideas from control systems. So the last piece I'll talk about just very briefly here, because I know we've only got about 20 minutes left, is using multiple measurements. So this connects back to what Mario was talking about at the beginning, where how can the non-intrusive load monitoring field leverage more things than just measurements within the house, right? So how can you kind of like move past the meter to the network and leverage things in the network to do a better job at energy disaggregation? So I'll talk about this in the context of the feeder energy disaggregation problem. But here what we're trying to do is say, instead of just having substation measurements, imagine we also have measurements across the network, but at points that aren't necessarily points you choose. Like maybe there are certain key points in the network where you're monitoring voltage because you've traditionally had problems there. But now you have that measurement. Can you leverage it in your energy disaggregation algorithm? Also, can you leverage smart meter measurements that might be coming at different sorts of resolutions every hour, every 15 minutes, every 30 minutes, something like that, and weather measurements? So how do you take all the existing measurements across the feeder, plus what you have at the house, together to do disaggregation. And this is a paper we just have published on transactions and power systems. So here are all the possible measurements we look at in this paper. The key thing is, instead of just measuring power at the substation, we're getting complex power. So complex power, complex current, complex voltage. So the real and reactive part of power. Real and active real and reactive, active and reactive is the same thing. But having that complex value sort of helps us immensely, and I'll show you later what the results show. But we're also looking at smart meter measurements that could be at different sorts of resolutions. So the approach is very similar to before, so I'm not going to go through every single detail, but the dynamic mirror descent part is basically the same. Now we have lots of measurements across the system, so we have to apply some kind of sensor fusion to basically combine them all together and use them together. And then developing output equations corresponding to each measurement so that we can bring them into this common framework in dynamic mirror descent. That was the hard part of this, because we're measuring things in terms of power, voltage, current, at different resolutions and time steps, but also that are affecting different portions of the system. So here we define portions of feeders, and here we can have like a node 0 is a substation, but then it branches into multiple different areas of the network. And in each area, there might be a set of households, but the measurements correspond to portions. So each of these colors is a portion. So how do you bring those back into a single output equation? That was sort of the part we had to spend a lot of time thinking about, how to do that effectively while keeping the framework still tractable. So in any case, I'll skip through the nitty gritties there because it's mostly just a lot of manipulating power flow equations and talk about the case study we did here, where we compare a variety of different measurements we might have from the system here through a variety of different case scenarios, so that we can investigate the value of including these additional measurements and which measurements are more valuable than others, and at what resolution in terms of time sampling. And so we assume we have a network that looks like this. And the substation has the substation measurement, but then there's different points in the network that have other measurements as well. So just example results to sort of visualize what we did. The top is the air conditioner prediction. The gray line is the actual air conditioner consumption. And then here I'm just showing two scenarios. The red one is we have no real-time measurements, so we're just using the models for open loop prediction. The blue one is we do have measurements, specifically substation complex current. So before we assumed we had real power only. With complex current, it's like we're having real and reactive power. So it's like a second measurement there, which is helping us immensely. So you can see the blue line is more consistent with the gray line. And more tables with too much information, but I will focus your eyes on the important parts. So here we're predicting the air conditioner, trying to predict the air conditioner power, reactive power, apparent power. So that's real power, reactive power, apparent power of the aggregate air conditioners. But what I'm actually showing you here isn't the prediction, it's the root mean squared error for each approach. So we want the errors to be as small as possible in this. So what we can do by comparing different things is see the value of adding additional measurements. So this is showing, the first one is showing the case where we have no real-time measurements, we're doing open loop prediction. And then the second case is showing if we have complex current at the substation. So just having that one measurement at the substation, but of complex current, so you have real and reactive power, essentially, but you have the real part and the imaginary part of the current, we can drastically reduce the error. So there's a huge advantage to having that one measurement. And then here, what we're showing is if we have complex current versus real power. So the previous case studies assume we just had that one real power measurement. And so we were getting an error of like 129. But if we instead measure complex current, which is sort of trivial to do at the substation, so we get two pieces of information instead of one, the error goes down to 64. So you can drastically improve your performance. Here is showing the value of smart meter measurements. So this is a case where we have a smart meter measurements, but we don't have complex current at the substation. And you can see all of these are with substation, all of these are smart meter measurements. But here we have it at 60-minute resolution, 30-minute resolution, 15-minute resolution. And as you increase the resolution of the smart meter measurements, you do better, but maybe not as much better as you would hope by having to collect the data at much higher frequency. And here's the value of smart meter measurements when you additionally are using the complex current measured at the substation. So you can see that complex current plus smart meter measurements, you can do very, very well. And if those measurements are coming at 15-minute intervals instead of at 60, you can do much better. And that's sort of the best you can do in this setting that we investigated. And here's the value of including complex voltage measurements. So here's without voltage measured at I think it's 1 bus in the network versus here. So voltage actually doesn't get you too much. If you have voltage measurements in your network, you may as well use them, but you probably wouldn't purposely put voltage sensors at various nodes in your network to improve your estimate. It's better to get smart meter measurements, even if they're very low resolution. So conclusion. So first, just some conclusions on this last part where I talked in depth about our approaches to use dynamic mirror descent and dynamic fixed share. These algorithms allow us to solve feeder energy disaggregation problems. And what's nice about them is you can use all these different models of the system and they don't have to be of a particular form like linear. What we find is that the empirical results are often comparable to the best, or at least the average Kalman filter approach, our benchmark approach in these cases, but you have no guarantees on this. But like I mentioned, that benchmarking we did was for a case that wasn't fully tuned. And then the initial case I showed you also, we weren't leveraging additional measurements in the network. And hopefully I've convinced you that both of those things help immensely in improving the performance. I also mentioned that we can use ideas from control systems, specifically Kalman filtering, to improve these sort of machine learning approaches. And we can extend the approach to cases where you have measurements across the power network. So with that, I'll end and I'll say, power systems needs you guys, non-intrusive load monitoring. I didn't go into details here, but I mean, we're solving this aggregate problem of trying to do energy disaggregation at the feeder, but we're also assuming smart meter measurements. And what we're actually assuming is with those smart meter measurements, we're doing non-intrusive load monitoring to the air conditioners. And that part is already baked into the algorithms. So we assume that exists and we know you can do it. And we're just leveraging it, assuming that we don't have to solve that problem ourselves. But there's so many other ways in which we could combine forces and solve really cool problems across the field. So with that, I'll stop and thank you very much for your attention.